Okay, so in the last few lectures, we've covered a lot of the basic outline of statistical mechanics. It's time for a summary, so we can put all the things we've covered already into one place where everybody can see. But then the next thing we're going to do is start applying all this stuff to molecular properties, ideal gases first, and then more complicated systems later. So far, what we've learned is that if you take some complicated system, molecular system, and run it according to the laws of mechanics, of physics, you'll get some complicated trajectory in phase space that fills up phase space, basically. And that serves as justification for the ergodic hypothesis, which says two things, two equivalent things, really. One is that all the possible microstates, all the possible systems, all the possible microstates of the system have equal probability, whether those microstates are classical microstates, P's and Q's, momenta and positions, or whether they're quantum microstates, spins or energy states or whatever. The ergodic hypothesis says they all have equal probability. It also says that if you are doing something experimental, where you're making some measurement repeatedly, and then you time average those results, then that should give you the same result, if you do enough of it anyway, to equal what you would get if you just averaged over all the possible microstates of the system. And both of those things together, the ergodic hypothesis stated either way, is led immediately to our understanding of probability for an isolated system, which says that the probability of any one microstate is just 1 over the number of microstates that are available. If they all have equal probability, then the probability of getting any one of them is just 1 over however many there are. And on the other hand, if you are thinking about not one microstate, but some set S of microstates, then the probability is just the fraction of all possible microstates that's occupied by the set S. We saw also that there is this absolutely important connection to thermodynamics that says that the number of microstates available to an isolated system where energy, volume, and mole numbers are being conserved is just the entropy basically is just the log of W. And from the entropy for a system, for an isolated system, you can then get all the thermodynamic properties. I didn't say this before, but it's worth saying now that this whole isolated system stuff is collectively called the microcanonical ensemble. The book talks about ensembles of various courses. I don't think various types. I don't think they use the term microcanonical ensemble, but anyway, in other books and in the wider literature, this situation is called the microcanonical ensemble. And W itself is called the microcanonical partition function. We saw before that Q is called the canonical partition function. Well, W is called the microcanonical partition function. Then we considered a situation where there's a system, it's in contact with a T-bath, but that's the only way in which it's open to the surroundings. So it still has fixed volume and fixed mole numbers, and so we'll call that a T-bath open system. Then we saw that the probability for one microstate in that case is given by the Boltzmann distribution, e to the minus beta energy of that microstate divided by this quantity Q, the canonical partition function. Down here is the name. And we've seen first of all that the probabilities are important. We can use that to get some feeling for how likely you are to see any one given microstate of a system. But the Q itself, the canonical partition function, is also important. And I'll say more about that down here. I didn't say this stuff before, but let me just say it now. Let's suppose you want to know in this case, for this canonical ensemble, let's suppose you want to know the probability not of a single microstate, but of a set of microstates, then the formula for that is essentially the same thing as for the microcanonical case up above, except that where you had W's for the microcanonical case, you have Q's for the canonical case. So you calculate a partition function in that case, where instead of summing over all microstates, you sum only over some set of microstates. So you want to know the probability of a set S, just do a canonical partition function, but sum only over the set S instead of over all microstates, and then take the ratio of those two Q's, and you get essentially the fraction again of microstates in the set over the fraction of microstates in all, for the whole system. An example of that we've actually used already, but didn't identify this way, is where we're trying to calculate the probability of finding a particular energy rather than a particular specific microstate. In that case, this numerator here just becomes the number of system microstates that have energy E times e to the minus beta E, and then divided by the partition function for the whole set, for the whole system. All right. Probably the most important results, well, at least as important as the probabilities above, are all the connections to thermodynamics for the canonical ensemble. And those are, first of all, the Helmholtz free energy, which is just minus kT log Q, and therefore is very similar to the entropy relationship that we had for the microcanonical ensemble. We also got a couple of other connections. The energy for the thermodynamic energy for a system U is just the same thing as the average energy for the system, and that can be calculated conveniently by just taking a derivative of the logarithm of the canonical partition function Q. Taking a derivative of that once more gives you the heat capacity, but we also saw that that's related to a statistical parameter, the variance or the width in the distribution of energies that are available to the system, and that variance can be calculated conveniently by just taking two derivatives of the log of the canonical partition function. And again, all of this stuff falls under the heading of the canonical ensemble, and the quantity Q that's sort of central to everything is called the canonical partition function. Okay, we've seen all of that already. We haven't really seen much in the way of application of it, but we'll see that now. That's where we're going now. But before we do that, let me just point out that there are other ensembles and other partition functions. We're not going to talk about them in this semester, but it's good that you know that they exist so that when they come up in your reading or in other classes later, or if you go to graduate school, they come up in a graduate class, say, that you've heard about them at least. And so another possible ensemble is one where the system is open to both pressure and temperature baths. That's the situation that we've seen before where Gibbs free energy is the most important quantity, and indeed there is a relationship between the Gibbs free energy and a new type of partition function, the isothermal isobaric partition function. That's essentially the same as the relationship between the canonical partition function and the Helmholtz free energy. So in all these cases, you can see down here for the next partition function too, we have some kind of free energy, some kind of partition function, and the free energy is basically just the log of the partition function for each of these cases. So yes, in the last case, you've got, again, two baths, one for chemical potential and one for temperature. And that's called the grand canonical ensemble. There's a grand canonical free energy, and there's a grand canonical partition function, and they're related to each other by means of a log, essentially. Okay, again, I won't say anything more about that in the rest of this semester. That's just for your information so that when you see it again, you'll at least have heard of it. Next thing we're going to do then is start applying all this to molecules and to systems of chemical interest. And the simplest of those are ideal gases. The stuff we've learned about already, the basics that we've covered already, apply to absolutely anything. If we wanted to, we could use those very same basics to deal, for example, with proteins in aqueous solution. We could put in DNA, we could put in polymers, we could put in drugs, we could put in anything we wanted, ions, whatever. Could make the most complicated system imaginable. All the ideas, all the relationships that we talked about above would work, in principle at least, for all those things. But those kinds of cases are really hard to deal with in practice. The principles are good, but in practice, very hard to apply. So we're going to start with ideal gases. Ideal gases are way easier, and we'll see why. The next thing we're going to talk about is the main reason why ideal gases are so nice. Here's a basic statement of what makes an ideal gas nice. Of course, we kind of already know this already, but ideal gas molecules don't interact with each other, and that makes them independent, physically independent, but that also makes them statistically independent. We talked about statistical independence a little bit in the last lecture. Here it comes up again. What does statistical independence, or physical independence, in this case they're the same thing, what does that mean? It means that the energy for each and every microstate that you're summing over when you're summing up a canonical partition function, for example, can be written as a sum of energies for each of the little subsystems inside of it, for each molecule, in the case of an ideal gas. And furthermore, that each of those terms in the sum depends only on its own variables, right? The Q1s that I have here, that's the variables that this energy E1 depends on. Those are different variables from the ones from the next term, and different variables for all the other terms as well. As long as the total energy of one microstate is a sum of terms, and each of the terms depends on different variables, then you have independent subsystems. And here's the general rule. Independent subsystems are really nice, and here's why. Whenever two or more subsystems are independent, the partition function factors into two or more parts. So here I have some energy Eij, depends on two different indices, and the total energy is just an energy that depends on the first index, and then another energy that depends only on the second index. That means they're independent of each other. That means all the microstates are indexed by two separate integers in this case. When that's true, you can show mathematically fairly easily, we could do it here, but I won't bother, that the total partition function for the full system is just a partition function for subsystem number 1 times a partition function for subsystem number 2. And you compute those two partition functions for subsystem number 1 by just ignoring the other subsystem and computing that partition function as if it were the only one. And then doing the same thing for the other partition function as well. You just sum up all the microstates that are in subsystem number 1, ignoring subsystem number 2. That gives you Q1. Then you do the same thing with subsystem number 2, ignoring subsystem 1, and that gives you Q2. All right. In the case of an ideal gas, every single molecule is an independent subsystem, which means you don't just have two Qs like this. You've got a Q for each and every molecule. And the full partition function for the whole set of, Avogadro's number, that n is large usually. So Avogadro's number, let's say, of gas molecules, there's just one partition function for each one of them, and you multiply them all together, and that gives you the overall partition function for the entire gas at once. And when you go to compute each of those little q partition functions, you just sum over the microstates for one molecule at a time. So you don't have to start considering all the possible arrangements of all the molecules in space, for example, or all their momenta and kinetic energies all at once. You can just ignore all the other molecules. They don't interact. And so all you have to do is sum over the microstates of any one molecule, do that for each molecule in turn, and then multiply them all together, and you've got the overall thing. All right. For most ideal gases, if it's not a mixture of two different gases, if it's a pure gas, let's say pure argon or pure methane or pure water vapor, then every one of these molecular partition functions is going to be a sum over the same sets of states for a water molecule, let's say, and that means they're all going to be the same. And that means this big product is just going to be a power. The overall partition function is just the Q for one molecule, one water molecule, let's say, to the nth power, where n is the number of molecules in your system. So even simpler in that case. However, there is one slight complication, and that's that this relationship is only true for distinguishable molecules, or distinguishable subsystems, in this case molecules. Distinguishable means that there's some experimental way that we could tell them apart. If you're in a gas and you somehow grab one molecule in the gas, can you tell which molecule it is? There's no numbers on them, right? There's no labels on those molecules. You don't know which molecule you've gotten. If you let it go and grab another one, did you get the same molecule back again, or did you get a different one? You don't know. That means they're indistinguishable. The cases where you have distinguishable molecules are rarer than the cases where they're indistinguishable. This rule only works when they're distinguishable. What cases are those like? Well, let's suppose your molecules are pinned down to a surface and they can't move. In that case, you can distinguish molecule 1 from molecule 2 and molecule 3. You could number them, in fact, by putting little marks next to them on the surface or something, and then they'd be distinguishable. Likewise, if you have a whole bunch of atoms or molecules all arranged in a crystal, you could, in principle, I suppose, put some kind of mark that says, this is molecule number 1, this is molecule number 10, or whatever, and they would be distinguishable because they're spread out and stuck at particular locations in space. They're distinguishable by their positions in space, and there are other ways in which molecules can be distinguishable too. But none of those things apply in the case of an ideal gas. In the case of an ideal gas, the molecules are moving around, and you really can't tell. There's no mechanism for knowing which molecule you have if you are looking at one particular one. So in that case, they're indistinguishable. And in that case, there's this issue, which I brought up way early in the class, but let's talk about it again. Let's suppose I have 4 molecules here, labeled 1, 2, 3, and 4, with numbers, but those numbers aren't really there, right? I put those numbers on there for our purposes, but those aren't really on the real molecules, which means that if I scramble the numbers, so 2, 1, 4, and 3 here, I don't have a different arrangement. I have the same arrangement. These two guys aren't two different arrangements. They're the same arrangement, and that's true for any other scrambling of the numbers. There are n factorial ways to scramble n numbers. So if I have n molecules and I number them all, there are n factorial ways of rearranging all those numbers. All those rearrangements are invalid if we're counting configurations, if we're counting distinguishable configurations. They're all one configuration. They're not n factorial configurations. And that means that what we need to do when we're calculating Q here is, first of all, multiply all the molecular Q's together, but then we need to divide by n factorial to take care of the overcount that we got by treating them as if they were distinguishable. So that n factorial makes them indistinguishable effectively for our purposes. So this is the formula we're going to mostly use. This is the relationship for the partition function of n molecules, all in terms of the partition function for just one molecule. We've made a lot of progress, that means. We've broken things down from having to deal with Avogadro's number of molecules to having to deal with just one molecule, right? We just need to get that little Q for one molecule now instead of getting everything for the whole thing. So let's now talk about these. That little Q is called a molecular partition function. And let's talk about those. So, a molecular partition function is certainly easier to deal with than the partition function for an entire array of Avogadro's number of molecules, but it is still, in principle, a fairly complicated thing. What goes on inside a molecule, there's a lot that goes on inside a molecule, so there's a lot that goes into this Q. what can we say about it? Well, it turns out we can say a lot. And the very first thing we're going to say is that even though the molecule is complicated, an awful lot of what goes on can also be considered to be a bunch of independent subsystems. So a molecule has a bunch of independent subsystems inside it. And what are those subsystems? Well, they're ones everybody's familiar with. First of all, there's translations. We can move the molecule around. There's a momentum associated with that. There's kinetic energy associated with that momentum. We could write a quantum Hamiltonian. This could be a quantum Hamiltonian just associated with the overall motion of the center of mass for the molecule. And if we did that, we could consider, for example, all our molecules to be inside of a box with volume V. That's the way we'd think about things if this were a thermodynamic system, and it is a thermodynamic system, so that's the way we should think about it. Then we could consider each and every molecule to be a particle in a box. That's going to be our model. And then we could solve that model, and if we did, it's already been solved, of course, then we could write down the energy for each and every particle in a box quantum state for a three-dimensional particle in a box. And if we did that, here's would be the energy. All these numbers here are integers. They're quantum numbers, of course. And so now we've got a whole bunch of quantum energies labeling quantum states for the translational degrees of freedom for our molecule, our single molecule. Then we can do the same thing for the rotations of the molecule. The molecule can rotate around its center of mass, right? Now the center of mass becomes the rotation center for the rotations. We can write a quantum Hamiltonian for that. Now it depends on, rather than the linear momentum squared, it depends on the angular momentum, L squared. And instead of divided by 2 times mass, it's divided by 2 times the moment of inertia. Moment of inertia is basically mass for a rotation instead of mass for a linear translation. And again, that's pure kinetic energy, but again, there's a set of quantum states, there's a set of wave functions associated with that, but we don't need the wave functions. What we need are the energies, so we can sum up a Boltzmann sum. And the energies in that case have a quantum number L, which goes from 0 to infinity. And for every quantum number, we can calculate an energy. So again, we have a set of energies, and again, we can sum those up in a partition function. I won't talk right now about the moment of inertia or the reduced mass or any of those things, because we'll talk in more detail about this very case a little later when we do the whole thing. Then there's vibrations, internal stretches or changes of shape of the molecule, and there's a quantum Hamiltonian, a harmonic oscillator Hamiltonian for internal vibrations. For a single diatomic molecule like this, there's only one vibration. For a more complicated molecule, there's a whole bunch of normal modes of vibration, and again, we'll talk about that when we get there. But the ideas are the same no matter how many modes there are. And there's a set of quantum energies for those, harmonic oscillator, quantum energy levels, and so on. And again, we'll talk about those when we get there. And then finally, the last type of energy or motion is the electronic motion itself. There is, again, a quantum Hamiltonian for that. It's the electronic Hamiltonian that comes out of the Born-Oppenheimer approximation. It's complicated, so I didn't write it down. And it wouldn't be very illuminating even if I had written it down. And if you solve it, what you get out are the energy levels for the electronic states of a molecule. And it turns out that even though the electronic quantum mechanics is much more complicated than any of the other cases above, in the end, for statistical purposes, the electronic part of the partition function is actually simpler than for the other cases because there's only a few states, there's only a few quantum electronic states that actually matter. There's the ground state, and then there's a few excited states. And if you know those numbers, if you know the energies for those few states, then you can just sum up a few terms in a partition function, and that gives you the electronic contribution. So even though we normally think of the electronic case as being the complicated case, in fact, it's pretty much the simplest case in StatMech. All right, so what we're going to say about every molecule in our gas is that the overall Hamiltonian, quantum Hamiltonian for the whole molecule, is a sum of independent terms, a translational term, a rotational term, a vibrational term, and an electronic term, and every one of those terms depends on different coordinates, right? Depends on the position of the center of mass for translations. It depends on the angles of rotation for rotation. It depends on the stretching variable or compression variable for vibrations, and it depends on all the electronic positions for the electronic Hamiltonian. But we're going to pretend at least that every one of these guys is independent of all the others. Now, that isn't totally true. Turns out that they are a little bit coupled to each other. You really can't vibrate, or you really can't rotate, for example, without also affecting the vibrations. But that's the approximation we're going to make. It's a good one. It makes things much simpler. It does cause us some small errors, but we can live with those errors, especially given that it makes the whole problem just enormously more easy to work with than without making that approximation. Okay, with that approximation then, the energy of each microstate in our partition function is again just a sum of terms, one for translation, one for rotation, one for vibration, one for electronic degrees of freedom. And we have expressions and quantum numbers for each and every one of those now. And furthermore, by the overall rule, these are all independent subsystems, which means that the overall molecular Hamiltonian is just a product of, partition function is just a product of partition functions, one for each of the little independent subsystems. So now all we got to do is go down the list. We calculate a translational partition function, a rotational one, a vibrational one, an electronic one, and we're done. A few comments on this approximation that we've just made, and then we'll pass on to the main work. The first is that yes, the translational factor here in the overall molecular partition function, that really is rigorously independent of all the others. You can break that out on paper mathematically rigorously, so this one really does separate, and there's no approximation there. But the rotations are coupled to the vibrations because when you rotate, you are affecting the bond length by centrifugal forces, right? You're stretching the molecule a little bit, and that affects the vibrations, but also because if the thing is vibrating, that's affecting the moment of inertia, right? The moment of inertia depends on the reduced mass and the bond length, and the bond length is changing if it's vibrating. Therefore, the vibrations and rotations aren't really independent of each other, but the effect is small. And so, yeah, the vibrations also aren't independent of the rotations for the same reason. And then also for the electronic degrees of freedom, if you're vibrating and if you're rotating, then you're moving the nuclei, and that affects how the electrons move. And so, yes, there are couplings between the rotations and the vibrations and the electronic degrees of freedom also, but again, these are small effects. And they're mainly small effects because each of these types of motion occurs on a time scale that's quite different. The rotations are much slower than the vibrations, and the vibrations are much slower than the electronic motions. And so they're roughly, to a 10% sort of level, they're roughly independent of each other. All right. That brings us to the translational partition function, which is our next topic, and we'll cover that in the next lecture.